So I'm going to start recording. Okay. So let me just full screen mode. Sorry about the technical hiccups. Please let me know if you have any issues hearing me or seeing the slides, because I can't see your comments while I'm looking at my slides, please. Okay, so welcome to this course now, finally, on this introduction to machine learning for physicists. The lectures were intended to be in a room in IFIC. So they were supposed to be with all of us together, but of course this is not possible anymore. They were originally scheduled to be 3 hours, with the idea that we will have I will just explain some things at the beginning of the lecture, and then we'll spend the rest of the time doing some hands-on work. So you will be with your laptops, working together in groups, and I will go around and just help you out when needed. This is not possible, but I like to keep some level of, let's say, intensity in what we are doing now, which is this remote version of the course. I think when I will explain the different aspects of machine learning I want to tell you about, it would be great that immediately you start working on the practical aspects on how to implement them. And yeah, I always think there is no moment than now when you want to do something. So what I thought is to run the course in a modified way. So the first hour of our course, 10 to 11, will be the lecture, so my explanations and so on, and any questions you have. Then from 11 to 12:30, we will all do offline work. The idea is that you can collaborate. Probably you know some of, there are most of you are students and you know each other to some extent, so you can maybe form groups and help each other, like it would have happened in the original version. And at 12:30, for about half an hour, we will reconvene. And one of the students, will present their results. Okay? So that's the way we are going to run the lectures. Any questions I can hear? No? Again, if you have any questions, just interrupt me. Don't be shy. Really, I think it's great if I hear somebody. Otherwise, I think I'm talking to myself. It's a bit worrisome. Okay. So at 12:30, we meet again. Not today, because today is a very short lecture, but the rest of the days, yes. After you have done your work, and one of you will just present what they've done, what they understood, and so on. Okay. The methodology. So there are many ways to teach this kind of course, of course, and the area of machine learning is extremely broad, even when you nail into the applications in physics. So what I'm going to do is to follow what is called a case-based learning method, which is what I like best. The idea is that you learn through example. I will tell you some generic features about specific methods in machine learning, but we will immediately move on into applying it to things. Because I think to have a specific problem to solve always helps you focusing on the problem. Okay, for example, when in each of the sessions, each of the days, we will learn a particular aspect of machine learning. For example, classification or computer vision, the issue of data sets when there is an imbalance of different categories, anomaly detection, and so many others, okay? And instead of talking about classification in general, we will tackle a specific problem. What I will do is to provide for each of these specific problems a basic notebook, which will allow you to start working on your own solution. These notebooks will be in the context of Jupyter, and we will be coding in Python. The type of frameworks we will use for computation in machine learning will be two: TensorFlow and PyTorch. you don't know anything I'm talking about, if you never heard about TensorFlow, PyTorch, or Jupyter, please do not worry. The idea is to precisely learn all these things. The practical aspects of the course. Okay, so for each lesson, I will share this notebook in what is called Google Colab. So I will give you a notebook that is already filled with some entries. You will do your own copy, and inside Google Colab, you can run the notebook. The idea of Google Colab is that it's a kind of computer, offline computer or remote computer that you can use. Google Colab allows you to also use their GPUs, their RAM, their memory. At least for education purposes, they are quite useful. So if you haven't done so before, please do sign up for Google Colab. Here you have the link, and if you click on it, on the PDF, it will bring you there. While we work on our solutions, I would recommend chat with me, sending questions, or with other students using Slack. You can join the Slack group. If you have never used Slack, please do, because it's pretty, right now I cannot see it, doesn't matter, useful and quite widespread when it comes to collaborative work. So you just link on, sign up for Slack, and you click here, you'll be able to join this group. And there as well, you can start even forming your own little groups of people that you know and you want to talk to remotely. Instead of using Skype or whatever you use, you can also use Slack. And again, if your coding background isn't great, please do not despair. That's the point of this course. We remember that we are not computer scientists, or at least most of us aren't, and we mostly learn concepts and develop tools and use computing as a way of helping us to do so. It's not like it's the base. Our basis is to actually code things. And what is especially for machine learning is that at the level of things we do, a lot of coding issues can be solved by just Googling, because there are so many people that are trying the same kind of things. And whenever they run into trouble, they go and ask in some forum, and somebody is nice enough to answer their questions. So you can use all this inherited knowledge by just Googling, which is what I do most of the time. So okay. Now, the rest of the lecture, I told you probably too many practical things. If you never heard about any Jupyter, TensorFlow, and so on, it might sound a bit scary. But this lecture is not going to be directly practical issues. We are actually going to think about what we are going to do in general. What we want to do is to teach a machine how to think. We want this machine, this, if you want, computer quote-unquote program, to develop the same or better understanding of problems, and to be able to perform tasks consistently and at great speed. So you think about it, what we are going to be able to do is something quite awesome. Okay, it's like I will say that if you just tell somebody outside our area that this is what you are doing, there you can. It's really say something that is very interesting. But you are going to find yourself at the end of this course having gone through lots of details, debugging syntax errors, preparing data, which is what you usually spend most of your time in real situations. And this initial concept that we are actually teaching a machine how to think, it gets lost somehow. And I think it's important to at least start with thinking about it. Because when you start posing a problem in machine learning, and when you realize that something is not right in the way you are doing it, often comes back to the initial point, which is, how am I teaching a machine to think? So if we take a step back, the first thing we can do is to try to just think about how humans and machines can learn. And the thing we know for sure is how humans learn, right? We learn from previous experience. Things that happen to us allow us to, for example, evaluate this previous experience and predict the evolution of a situation. Given what I've seen before and given the current conditions, I expect that such and such will happen. And you, in your mind, give some level of probability to this or that possibility happening. You think this is likely, you think this is not likely. Given that most of you are scientists, this comes to you naturally by training, but even if you were not, you didn't have a, let's say, a scientific background, you will still assign some level of probability, hope if you want, or belief, but still you will try to predict what will happen next. And this all the time, even without realizing. Also, when you start thinking about what happened before, something that, especially if it's something that worries you or interests you, that you focus on, you start discovering unknown relations among maybe the actors in whatever your memories are, or the different external inputs that change the way things happen in the past. Also, very typical of us, especially among scientists, is the idea that given a set of boundary conditions, let's say the situation I'm in right now and the ability I have to call for resources or make choices, try to find, or we tend to try to find the different choices, options that will maximize a particular return. Very typical, I don't know about you, but for me, is I tend to choose the set of options that minimizes the amount of effort I have to do, especially if I don't care about something. And sometimes I will choose different paths depending on whether I want to be able to spend the maximum amount of time doing something that I care about. Those choices, how to combine them, what to do, what not to do, and when, those tend to be complicated, even if we don't even think about them. They just come through our mind and we make choices without even realizing that behind there is a lot of analysis of the different interactions, if you want, between the choices. Same as playing chess, right? You always try to think a few steps ahead. But something that is even more amazing about the way we humans learn is that based on this previous experience, based on the stuff we saw before, we are able to arrive to a level of abstraction, a higher abstraction if you want, in which we can imagine new possibilities, completely new possibilities, where the situations, the players are maybe things that we have not seen before. Okay, for example, why I put this picture of Einstein and Bohr, just to, I guess, also to show you graphically what kind of, when we humans think, we don't think sitting in front of our computer and thinking linearly, let's say. The thing in terms of when it comes to humans is often in this kind of a sparse way in which ideas are floating, a discussion happens, and the thinking evolves in a way that you will not be able to describe in a few sentences. And now if we come back to, again, Einstein and Bohr, and you think about the revolution of quantum physics, think that these people were able to describe nature at a level hadn't been seen before. Even at a level that nowadays it will be difficult to represent or to visualize intuitively, because the quantum world is so detached from our everyday experience. Yet these people were able to talk, discuss, and evaluate what kind of possibilities nature there could be in this quantum level. But what they were doing at the end of the day was taking common language that they have developed an intuition for. For example, they use the language they had of mechanics or wave phenomena, statistics, and so on, to try to describe objects related to the quantum world in terms of these well-known objects. For example, when you learn quantum physics, one of the concepts that appears is this concept of probability, right? And the wave function and the collapse of the wave function and the equations, right, that you write. You then try to interpret them and talk about them, develop a language that is based on something you knew before from doing mechanics, from doing statistical mechanics, and so on. What we do as humans, what is really quite amazing, is our ability to do transfer knowledge, which is given a previous experience, a previous ability to develop an intuition and a language to be able to describe phenomena. We are able to transfer it to something that is completely new. We can imagine new possibilities. And we would like the machines to be able to do the same. So I think we can all agree and tap on our backs and say that, of course, this is all very impressive. Humans, we populated the earth, we are able to dominate, everything, except when we screw up with climate change and so on, and pandemia that we cannot control. But what we also know is that humans, and then our learning, is very limited. It's limited even in the case of these very impressive individuals like Einstein, because even Einstein and capacity to think and to analyze situations and so on, he was limited, like anybody is, by his own personal viewpoint. The experiences he had, the opinions he formed, and so on, were also giving him a particular funnel view of what he was able to think and what he wasn't. And this happens to everybody. Maybe for Einstein it was less than for us, but it happens to everybody. We are limited by this personal viewpoint. And even when we are quite open-minded, we are still limited by what I would say is a collective intelligence. People living in different areas of the world with different environments, they will have different ways of thinking about stuff, and also their ability to generalize or to move from that experience. And also there is this inherent capacity to process information, which is limited as well. The amount, the speed, and at the same time, the level of detail we are able to process is also quite. On the other hand, when it comes to machines, the real ultimate limitations of those machines are not yet known. The technology and the way we deal with them are still evolving. We have gone from the use of CPUs. 10 years ago, it started with the GPUs. Now they are completely, ever present in the context of machine learning. TPUs are already here. FPGAs, if you don't know them, is just different architectures for computation. So like a hardware, essentially. And even beyond that, there is also different ways in which we can compute things. The classical computers we use might be, superseded by computers that are made from other structures, like quantum computing or neurophotonics, that can change again radically the way machines are able to learn. If you have any questions, if not, I'll go ahead. But you are still there, right? Yes, great. Perfect. Now, we have this course today, and many people sign up, I guess, because many of you realize that this is an interesting topic. And it's not by chance. We are really, in terms of what is machine learning in the middle of a revolution. I know that in physics we say revolution too often, and it gets a bit dusty, the word, but it's really a revolution. Just not just because the hardware itself, the processing speed, the storing capacity have increased enormously in the last years, but also one thing that is leading to a revolution of what machines can do and how they can learn is precisely the way they learn. If you had done coding before, like when you were undergrads or whatever, what you will do traditionally will be to write lines of code. And you wanted a machine to learn. Think, for example, of robot, one of these robots that cleans the ground, right? These are kind of things that go around cleaning the ground, and whenever there is an obstacle, they stop, they turn back, and they keep moving. Until they see another obstacle, they stop, they come back, and they keep moving. These are kind of instructions that we can code, like what you see there. If something is in the way, then you stop moving, otherwise you continue moving. So the learning of this robot is just given by this code. The robot might also learn the different parts in the house and realize that when it arrives there will always be an obstacle, so it has to go back and not get to that obstacle, and so on. But the learning itself, how much it can learn and in what context, is always limited by being able to write these lines of code. And we can write extremely complex programs. For example, this is a kind of snapshot of the coding that will go behind a very, very, very simple game. But a game where you can perform very many tasks and take many, many options, but still the structure you want, the way in which you can think, is always based on those lines of codes, on ifs and do's and so on. So in other words, while we are hard coding instructions and asking the machine to learn, we are not allowing the machine to describe anything that we haven't encoded in. It's like if you, and this is, by the way, not what we want the machine to do. We don't want to, we want the machine to learn by itself, to be able to acquire with more data, organically you want to be able to learn more without us having to redo the programming you want. But since if the machine is just based on lines of code, you are asking a machine then to behave like a born blind person who's asked to think of blue. Blue is an experience that only people with no visual impairment can experience, can describe, can even think of. Whereas a blind person doesn't know what is blue, doesn't know what colors are. I'm saying this, but I'm not blind, so I don't know. But just to give you an example, essentially what I want to tell you here is that if we want the machine to actually fly off and do something unexpected, we cannot keep just coding more and more complicated things. It needs to be done differently. And that's this revolution I want to tell you about. So this is a new way of thinking, if you want. It's based on neural networks. And it's not the only way in which you can allow a machine to go beyond your programming, but it's, let's say, the easiest and most prevalent right now. A neural network is a structure made of a very simple but non-linear unit called neuron and organized by layers, where a set of inputs are processed through this neural network, leading to outputs. The idea is that the neural network is going to learn from data with no specific instructions. You are not going to write a code where you say, go over the data, and when you see this, then you go that. No, you are just going to tell the network to maximize its ability to describe the data and to generalize it. That's all what you are going to do. The idea is that even starting with very simple units, these neurons, the fact that you are now interlacing them in many ways, as you see in all these connections among the neurons are these little balls of color, yellow, blue, and so on. This ability to interlace them will allow the network to explore relations between inputs and outputs that cannot be contained in lines of code. Also, the fact that they are all made of the same bricks, you want the neurons, they are all exactly the same. And it's also, they are also arranged in layers, allows the neural network to do this description of the data extremely fast. Now, I'm saying that this network will learn from data. And the meaning of learning is going to be very different depending on what you want to tackle, the problem you want to tackle. Sometimes learning will mean predicting the future. Sometimes learning will mean that the neural network is able to detect an anomaly or optimize a distribution problem, diagnose a disease, have a conversation with a human, or even understand asymmetry in a system, and many other meanings. So here learning is a concept that is very broad. Essentially, we are able to ask the machine to learn something, and this learning can be extremely broad. Okay, this machine learning and in general is called artificial intelligence technology. It's not new. The idea is obviously not new, but right now it's getting to be a disruptive technology. It's disruptive, apart from this buzzword, everybody likes to say disruptive, but what do I mean by disruptive? Here, what I mean is that we are unable right now, and probably never, to predict how fast it's going to evolve and the extent of its applications. And we are not able because if you look around, you will see that new algorithms, so ways of learning, and their applications appear every day. And this tendency of having more increase level of applications and ways of doing things doesn't seem to be slowing down. And as new technologies are going to appear, for example, a more prevalent use of FPGAs, whenever quantum computers are available, and I think also neurophotonics is going to also become as well a useful technology, these algorithms and these applications are just going to expand. So it's a disruptive technology. In general, it's called artificial intelligence. People, depending on where you are, tend to use this concept more just because for the public it seems to be a more catchy name. But artificial intelligence is just the idea that there is, or you are able to build a program that can feel, so external inputs, reason, act, and also adapt to the change of these external inputs. Within the artificial intelligence, there is this machine learning. Machine learning corresponds to an area of artificial intelligence of algorithms which can improve as they are exposed to more data. Okay, so they are, whereas artificial intelligence could be our robot that is going around cleaning the ground, machine learning will create a robot that is also able to realize, for example, when a person is moving and so on. It's able to improve as they have more data. And within machine learning and with the use of neural networks, we get also to the level of deep learning. And what is deep learning? Those are a type of the use of type of neural networks which can learn from a huge amount of data. Okay, so those are the concepts that are used and the differences. I'm almost done. So what I wanted to tell you finally is the kind of things that machines can do already as compared to humans. What they can do already are simple tasks. For example, computer vision, which took a long time, but is already here. It's something that we as humans, we don't think even that we are, how amazing is our capacity, not just ours, but of animals and so on, to be able to see, to identify objects, to draw conclusions and so on, based on on vision. And it took some time to be able to develop something similar for computers. So in that sense, I would call a simple task. A computer now can see. For us, as a human, it's a simple task. And now computers can do that task in a faster and more reliable way. And now computers can do a lot of very simple tasks on that way. And one of the advantages of computers then is that they do not tire, they are not easy to be corrupted, they don't accept bribes in general. And these kind of technologies where machines can substitute humans on simple tasks are, I would say, interesting because they might free out humans from low intellectual level tasks. And when people think about this AI revolution and how this is going to disrupt the job market and so on, often they are thinking about this first set of tasks that the machines can do. Tasks that are done by humans, that are repetitive, that needs to be done precisely and in a reliable way. They are not extremely complicated, but still they need to be done. For example, think on sorry, I have interruptions. Think on on a factory, and you have a line of work, and there are lots of workers there doing a job that is repetitive, and maybe teaching a machine to do it is not trivial, but once it's done, it can be done over and over again. But maybe for us as a scientist, a more interesting aspect of machine learning and machine intelligence is that they are able to digest huge amounts of data and take decisions or predict the future based on them. Whereas we humans have this lack of capacity to actually digest lots of data. So when you think, for example, how you work in complex problems, as scientists, you tend to do it in collaboration, precisely because it's useful to have different points of view and people that are able to retain important details that will become, they are able to be drawn back afterwards. In general, we as humans, as individuals, we are limited by this ability to digest data, and that's why we often form groups as well. Another thing that nowadays intelligent machines can do pretty well is to be taught to identify what is normal. And once they are trained into what is a normal behavior or normal expectation, normal distribution, and so on, they will be able to identify what is not normal. And the other aspect of intelligent machines that is also very interesting for us as scientists is that they can learn relations which could escape human perception just because those relations are subtle. So it could be that you are thinking on a physical system and this system is complex, you are influenced by many, many parameters, and to your physical intuition, there are a set of parameters that are important and others that are not. But machines, when you are teaching them to look for relations, they're able to look for evidence that is too sparse to be detected. For example, it could be that in your physical problem, there are a couple of parameters that are actually relevant, but only when you take them into account together. And in the way you are thinking about your physical problem, you are not thinking in that way and you are not seeing those relations because they are just too subtle in the description you are making. Machines should be good at picking up on those. Okay, so that's all I wanted to say for today. Today is a very light class. I don't want to scare anybody. The real world will start on Monday. But for the rest of the morning, what I would advise you to do is to go to Slack. At the beginning of the slides, you see the link. Just click on it. Join up, and then you will see I can see already students that sign up. And this is going to be our way of communicating while you are working on the notebooks. And at any point, you can always send questions to me and to others, okay? So this Slack channel will be a way of interacting. You also need to go to Google Colab and sign up. So you are able to run the notebooks. And if you want to work locally, and what I mean is in your own laptop or desktop, I will advise you to install Anaconda or Conda. It's a way of, or PEEP, or wherever you have in your system, something that allows you to install quickly libraries and dependencies that will appear a lot in this kind of analysis. Okay, so you Google it, and for your system, there will be a way of doing it. And if you have problems installing or whatever, send the questions to Slack because there is like 70 people, so I'm sure somebody will know the answer. And again, if you want to run locally, you need to install Jupyter Notebooks. And I will say that if you want to start going over some examples, I put here a link. You can click on it. And there are examples on physics, GR, and so on. So you can have a look, but please do not overdo it. You are going to be fed up at the end of this course of using Jupyter. So don't feel like during this weekend you need to understand everything about Jupyter and Python and so on. I will, pause and wait until Monday and do the real and intense work. So as I told you, every day we will be talking about a particular aspect of machine learning. The first one on Monday will be regression, because it is a very simple and intuitive way of thinking about describing data. We are going to learn other things. We are going to learn about reinforcement learning, anomalies. We are going to see how images and videos are analyzed and learned from machines. We are going to learn the concept of transfer learning. We will even talk about the use of machine learning to identify symmetries, to identify the equations of motion of systems, and we will finish with a bit about explainable artificial intelligence. Why? Because you are going to learn lots of tools during this course. You are going to be able to do a lot of very cool stuff. But at some point, you are also going to start worrying about the magic that goes behind this machine learning. It looks like you will see neural networks in particular are very, very expressive. So you will be able to describe very complex data in a way that is extremely precise, and yet you don't understand completely. The neural network does, in the sense that it's able to predict and generalize to other situations, but you don't. And as physicists, I'm sure you are going to feel very frustrated and you will think that this is not the way to go because obviously you don't like black boxes and you really want to understand what's going on. This is something that as physicists we feel because we want to understand, control, develop intuition and so on. We are not going to let a machine do all the thinking, but not just for us, also for policymakers, for the society in general, it's important to be able to develop tools to understand the decisions that machines will take. Think, for example, on how even now already companies hiring people, or insurance companies making decisions about the level of insurance, or banks about the loans they give or not, they are using artificial intelligence to do this. Why? Because it tends to make better predictions, is faster, and you can always blame the machine when the decision is not what the client wanted. But this is not going to be good enough. And there is already a lot of voices, talking about how we need to make sure that machines do not inherit the same level of biases that we as humans do. So there is all these issues about when we teach machine to take decisions, to make sure that this teaching is not, let's say, biased negatively against groups of individuals and so on, so that we don't introduce biases. So there is a lot of activity, interest, but not so much done in terms of explainable AI. It's good to use AI. It's an extremely powerful tool, but we need to also understand to some level what kind of thinking, quote unquote, has gone behind. So this is, again, not only useful for policymakers, it's also, I think, a call for us, for physicists, because we just don't like black boxes. So we'll finish, our last lesson will be on explainable AI. Okay, so I'm done with this. Do you have any questions? I'm going to stop sharing. And if not, please join Slack, start doing your homework, and we'll see each other on Monday, okay?
Sorry, can you hear me?
Yes, I hear you very well. Tell me.
Do you recommend to work locally, or is it all right to work on Google Colab?
I would recommend that everybody has Google Colab set up so they can run no matter what. But if you, for example, want to do, how to say, you're a bit more freaky, you also want to do local stuff.
Okay.
Because you have more control and you can install stuff. And Google Colab is great because it allows anybody to start running stuff. The problem is that all the issue of uploading folders, downloading folders, and so on is extremely annoying. So if you really want to do beyond this course, I would recommend doing locally as well.
Okay, thank you. Nice lecture.
Thank you. Okay, more questions? If not, have a nice weekend at home, I guess.
One question. What
Yes.
version of Python do you recommend? 3.7 or 2.7?
For Python?
Yeah.
Yeah, 3. Absolutely, 3.
Okay.
Forget about it's dead. Python 2 is
Yeah,
dead.
I know, but I don't know.
No, it's
okay.
2. It's many. There are many applications that still rely on Python, and you can set an environment for Python 2 if you need to. But I will only use Python 3. Okay.
Okay. Cool.
Cool. Any more questions of any kind? Okay. So see you. Bye.